So the real world is always going to be analog, and the processing will be digital, and then again we have to come back to analog. Like for example, let us say in a recording studio, a singer is singing a song and that is being recorded. Now that song has to transmit over a period. So let us say that there is a radio jockey who is saying something. Now just recording at that place won't work. That has to be transmitted to the receiver. So basically the transmission part is going to be digital, its own good reasons. And again, at the receiving end, we don't want to listen to a bit stream. If I tell you that the song, this is a song, if I tell you that this is a song, will you enjoy this? Only a bit stream? No. So this has to be converted back to analog. And that is why we always say that the real world is always analog. The processing and transmission can be digital, and then again things have to be converted back to analog. So this is basically the thing which you have to remember when it comes to digital design, that though you are talking about digital, the real world is always analog, but when it comes to processing and transmission, this is going to be digital. So as an engineer, we have to focus on this part, that is processing and transmission. This transmission part is actually addressed in a subject called as DCOM, or it is called as digital communication. So what we are going to mainly study is the processing part, how to make the data secure, how to encrypt it, how to make it suitable for transmission. All those things we are going to do in this course. Okay. So coming back to this slide, you can see that the first signal is a continuous signal. So it doesn't have any breaks in between. Doesn't have any breaks. The second signal is having constant amplitudes with fixed breaks. So basically this is like a sampling signal. So the first signal is called as a continuous signal. We will call it as signal A. The second signal is called as a pulsed carrier. Pulsed carrier means it is just a on off on off on off on off signal. The on value can be anything, but the off value is 0. So this is just a on off signal, commonly called as a pulsed carrier. Now you must understand, if I multiply the first signal with the second signal, I should get this. That means, let's say that here the unit amplitude is 1. 1 into anything here will be that signal itself. So we are capturing the value at certain instances of time. Now here, so this signal is actually this A into B. Can you understand this? This is nothing but A into B. So you can see that this signal is sampled at certain instances of time. Now the basic question comes, why should I sample? Why should I not use the signal as it is? Why should I not use this as it is? So the question again comes, like for example, if you buy 1 kg of rice, will you check every grain of rice, or you will just sample the things? I think you will sample, because what happens is, that it is practically not possible to check so many grains of rice. But at the same time, I don't want any black component coming inside that rice, which I will get it in my mouth when I actually cook and eat that rice. So with respect to that, we do some kind of sampling. So this is exactly what we are doing. In the context of the signal, it is difficult to store infinite values of the signal. When I say that, when I use the word store means I require some memory. So if I take infinite samples, I will require infinite memory, which is practically not possible. Our memories are finite. They may be in certain GBs, they may be in terabytes, but they are definitely not infinity. And that is why we have to focus on taking minimum number of samples. Now, after sampling, we need to quantize the signal. What is quantization? So let us say that this value is 2.2, this value is 3.1, this value is 2.2 again, this value is 1.5 something. So what we do is we approximate this value to the nearest integer. We are approximating this value to the nearest integer. So if this value is 2.2, this will become 2. If this is 3.1, this can become 3. Now you may ask me why not 4? So both are possible. In Excel also there is a function called as round up or round down. So you can round up to the nearest integer or you can round down to the nearest integer. But generally we don't keep a floating value. Now, after quantization, what we do is that we convert every value into bits. So you can see that 2 is represented using 2 bits. 3 is represented using 2 bits. 2 is represented again using 2 bits. 1 is represented again using 2 bits. 0 and 1. This 0 is again represented using 2 bits. 0 and 0. 1 is represented as 0 and 1. So we will come to these representations, what it is and how they have come and all later on. But what I mean to say is that you can see here the signal amplitude is constant, and each value here is converted into two more values. So one value in the continuous signal is converted to two values in the digital signal. So immediately you should be able to imply that the bandwidth required for the digital signal is going to be double as that of continuous signal in this case. Let us say that if I represent each value here with 3 bits, then the digital signal will be requiring 3 times the bandwidth, 3 times the bandwidth as compared to the continuous signal. So digitization comes at the expense of increased bandwidth, but though the bandwidth becomes high, today we have a lot of hardware and high speed processors which can process this data, and that is why digital is so much in the demand. Otherwise, truly speaking, digital requires a large bandwidth, but we have taken care of that using fiber optic cables. So this particular thing cannot work on its own. It requires a lot of support, and today we are able to provide that support. That is why most of the time we use digital signals. So again, coming back, we start with a continuous signal, then we sample this signal using pulsed carrier, and we call this signal as a discrete signal. Then the discrete signal is converted and quantized into fixed value signals. Now these fixed value signals are then converted into digital signal, that is this 2, 3, 2, 1, 0. These are 4 different values. So these 4 different values are converted into just 2 values, that is logic 1 and logic 0. So that is where we say that we have converted these analog values 2, 3, 2, 1, 0 into digital values, that is 1, 0, 1, 0, 1, 0, like that. So this is called as A to D conversion. from quantized signal to digital signal, we call it as A to D signal. Let us go ahead. This process, that is from continuous to discrete signal with the help of a pulsed carrier, is called as sampling. So the process that is used to convert analog to discrete is called as sampling. From sampling, from sampled signal, we do something called as quantization. So which is the next step? First is sampling. Second one is quantization. And after quantization, we convert the signal from analog, these are the fixed analog values, 2, 3, 2, 1, 0. Though they are fixed, we call them as analog because they are not logic 1 and logic 0. So by doing these three operations, sampling, quantization and A to D conversion, we can convert any continuous signal to a digital signal. So while converting, we should take care that we sample correctly. We don't take very huge number of samples. Huge number of samples means actually better representation of the signal. But it will also require more memory because you are sampling more. You will require more memory to store this signal. So your accuracy will improve, your quality of the signal will improve, but it will demand large memory. And many times large memory might not be available for processing. So that is why we need to optimize sampling. Similarly, we have to optimize quantization also. That means whether to represent this 2 using 2 bits or 3 bits or 4 bits or 5 bits. So that is also a question. So based on memory, we try to do this. But generally, we try to represent the numbers using as less number of bits as possible just to save the bandwidth. So I hope this much is clear. Karthik, is this much okay? Was everything audible?
Yes, sir. Everything was audible.
Okay. Now each domain, for example, we have continuous, we have pulsed, we have sample signals, we have quantized signals, we have digital signals. Now to process any signal, we require certain mathematics. Without mathematics, we really cannot talk about signal processing. So when it comes to continuous signals, we will generally speak about Laplace transforms, Fourier transforms, and Fourier series. So I think Laplace transforms and Fourier transforms in some or the other form have been introduced to. Then the next thing is when you go into a discrete domain, we are looking at Z transforms, discrete Fourier transform, and discrete Fourier series. When you look at quantized signal, there is some statistical theory involved because you are approximating, and statistical theory talks about approximating things. And the last one is Boolean algebra. So since our focus is a digital signal, what we need to look at is Boolean algebra. So our signal will be looking like this, that is, it will be logic 1 and logic zeros, and my focus will be Boolean algebra. So in short, what we will be dealing with is the input and output of my system will be digital, and the mathematics that I will use here is going to be Boolean algebra. I am not going to use Laplace, I am not going to use Z, I am not going to use Fourier or any even Fourier series, and neither statistics. I am going to digital domain has its own mathematics, and that is called as Boolean algebra. So the first two chapters will actually speak about Boolean algebra as such. So if you want, you can just note this down in short. I will wait for 5 minutes. Uh, I always believe that this kind of diagram should be there in the front page of your book, because it really speaks about how a signal is converted into a digital signal which we are going to work on. So we have continuous signal, then we have pulsed carriers. Again, we sample the signal, quantization. Sampling and quantization will decide how much memory will be consumed to store this signal. And then finally, if when we are okay that okay, the signal consumes good enough memory and not too big, large amount of memory, we go for processing the signal using some Boolean algebra. So I hope the focus of the course is very important. Probably when you are dealing with EDC, you will be using Laplace transforms. When you are dealing with electrical networks, I think you will be using Laplace transforms and Fourier series. And many times in signal processing, we also use Z transforms. But in digital, you will find that Boolean algebra is going to be the simplest as compared to Z, Laplace, or even Fourier. So in a way, this makes things simple, but that doesn't mean that the entire course is going to be very easy or something like that. Now, why digital? Why to even convert the signal into from analog to digital? So the first point there is that digital systems are generally easier to design. So what is the meaning of this? The circuits used in digital systems are switching circuits where exact value of voltage and current are not important. So we are not interested in the exact value of the signal. We are interested only in high and low. So you can see here that the signal is just 1 and 0, 1 and 0, 1 and 0. It is, we are not interested in how the signal varies. We are just interested in what is the digital equivalent of that signal at a particular instant of time. So that is very important. The digital systems are generally easier to design because we have to deal with only two levels, that is high and low. Whereas in analog, we have to deal with infinite levels. That is why designing of the amplifier is very critical. There we have to talk about bandwidth or fidelity, or there are many terms like that which talks about the signal integrity. But here we only talk about something called as signal to noise ratio, SNR, or noise margin. So next is information storage is easy. Now what do we mean by this? That we have memories which can store logic ones and logic zeros very easily, but we don't have memories which can store 5 volts, 3 volts, 3.3 volts, 1.1 volts. So we don't have memories that way. That is why it is important when it comes to storage of the signal, we want to convert it into digital. Think like this, that you have 1000 songs. I don't think you would like to listen to them. I don't think that you will like to listen to all the songs in one go. Probably you will listen to 10 songs, then maybe 10 songs on some other day, and so on. So it implies that storage is important with respect to processing of information, and that is the reason why we need to look at storage, and storage should be easy. It should not be very difficult. If we are not able to read and write to the memory very fast, then again the retrieval of the information becomes a problem. So again, those problems are there which are addressed in many different ways. Then we have accuracy and precision can be controlled. Now, what do you mean by accuracy? Accuracy means how accurate the result you are going to give. Again, you can see back here that here you are doing some kind of approximation and you are taking some number of samples. Now, if the user wants higher accuracy, he might be paying you more. So, if he pays you more, you should be able to control the accuracy of the system. If the user is not paying us good for what, then we may we should be able to reduce the accuracy of the system. Reduced accuracy means less hardware, and less hardware means less cost. So accuracy and precision are directly related to cost, and that is why this should be in our control. In analog, it is very difficult to control the accuracy and precision, whereas in digital, we can control how we sample, we can control how we actually convert from A to D. So we can control the number of bits required to represent a certain sample of the signal. In that way, we can control the accuracy and precision of the signal. So I hope these 3 points are very clear. Digital systems are generally easier to design. You can take down only the main points. Information storage is easy. Accuracy and precision can be controlled. Then next is operation can be programmed. That means it is fairly easy to design digital systems whose operation is controlled by a set of stored instructions, commonly called as the program. So you all must have done some kind of C programming by now, and you also know what is a program. A program is a systematic set of instructions, one after the another. If the order changes, then the systematicness can go away. So that is why it is important to store these signals in a certain, or arrange these instructions in a certain way to call it a program. So we can do programming when it comes to digital. We can program values to logic 1 and logic 0, but it is very difficult to program in analog. So there we cannot do that. Then we have digital circuits are less affected by noise. So like I said that the main values are logic 1 and logic 0 only. So let me highlight this particular point, that is less affected by noise. Means exactly what? So let us say that these are my bits, logic 1 0 1 0. Now I pass them through some channel, and on the other side I get something like this. So I get the one level which is corrupted by noise. Now what I can do is I can use a threshold. Now what I can do is I can use a threshold here and cut this signal off here, so that this much part goes away and we get a flat portion of this signal. So in a way, less affected by noise means filtering is easy. So that is how you should take it. Then we have digital circuitry can be easily fabricated onto a chip. So I think yesterday in my lab session I showed you how exactly a circuit can be designed and taken on chip. So analog circuits are difficult to do that. So I will just explain that using an example. Limitations of digital technique are, so these were the advantages. That doesn't mean digital does not have any limitation. Like I told you, the real world is analog. Processing digitized signal can take times, and hence there is a need for high-speed microprocessors. So when you are talking about any digital technique, this is very evident, high speed. So certain processors that you might have studied is or worked with is Arduino. So the clock frequency is around 12 megahertz. RPi boards have a processor where the clock frequency is around 1 gigahertz. So this can process faster. And you have certain hardware called as FPGAs, which can go up from around 50 megahertz to 1 gigahertz. So it's a variable clock. You can vary the clock. So Again, I am highlighting that when you say you want to go digital, it means you need to do lot of processing, and to do lot of processing, you require high speed microprocessor. Karthik, was everything properly audible and visible?
Yes, sir. Both.
Okay. So this was the first part of my that is the basic introduction of the course. Now let me just shift to another slide. Okay, is this slide visible?
Yes. Yes, sir.
Okay. So now let us formally start with our first uh, topic, or rather subtopic, that is called as a number system. So what is a number system? Number system is a basis for counting various items. So how do you count? That is the question. Now I think you have started counting in school, right? So when you started counting, your teacher started from maybe one, two, three, and then maybe she went up to 10. Uh, I don't know about you, but I'll tell you my experience. My teacher started to teach me counting by telling me to look at my own fingers. And then she asked me, how many fingers do I have? So then I started counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I said 10. Okay. Then she asked me, how many toes do you have on your legs? So I again started counting the fingers, and it was 10. So that is why, since we are being told, or the most commonly used system is a system which has numbers from 1 to 10. So this number system is called as a decimal number system, where our teachers have also taught us something like this: thousands place, hundreds place, tens place, one place. So each number, so if I want to write 1561, I have to write it like this. So the place value of this one is 1, the place value of 6 is 10, the place value of 5 is 100, the place value of 1000 is 1 is 1000. So this was our basic number system. So that's what is the first thing. The usual base 10 or decimal number system was the first number system, and this is the same number system that we learnt in school. Now we wrote 1, 2, 3, 4 like this in a certain way. So we wrote 1 like this as a straight line. 2, we wrote it like a curve, a slant line, and then again a horizontal line. Then 3, we wrote it as two curves. 4, we wrote it probably as straight line, horizontal line, and then again horizontal line. So this was the way in which we wrote the numbers. Now, based on this theory, we did one more number system, that was Roman numerals. Have you all not done this? If you are not done this, if you have done this, type yes in the chat box. Have you seen Roman numeral systems? Okay, so I can see that. So 1 could also be written in this way. 2 could be written with 2 lines. 3 could be written with 3 lines. 4 could be written with one straight line and one V, and so on. So this was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, why are we even looking at this? We all know this, right? So just to give you a flair of how the number system has come up in the context of a computer. So the third number system that we now use is something called as a binary number system. So we have only two digits in this number system, that is 1 and 0. In the decimal number system, we have 10 digits, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then again we start with 1, 0, 1, 1, 1, 2, and so on. But in a binary number system, we have only two digits, 1 and 0. That's it. So we don't have more than that. So numbers, so when you have more number of digits, the size of your number reduces. But if you have a less number of digits, the size of your number is going to increase. And that is the reason why some other number systems have also been suggested. So this system of ones and zeros, so how do you read this? We read it as 101. How do you read this? 100. How do you read this? 11. Don't read it as 10-0. Wrong. Or don't read it as 1 and then 01. Don't read this as 11. That is wrong. So you have to read it as what? 1, 1. 1, 0. Don't read it as 10. Especially in the binary number system. So you must understand that if I write 1, 0 in binary, I will call it as 1, 0. But when I'm looking at decimal, the same 1, 0, I will call it as 10. So that is the difference. Okay. So we'll move ahead so that we get more clarity. So this binary system, why are we even studying this? This system is used in computers, and we will discuss this and the other systems of representing the numbers slightly later in this class. So the first number system. In general, the position of the digital system is represented by, so I want everybody to write this. I will wait for 5 minutes. I want everybody to write this. Number systems in general, the position of the digital system is represented by n is equal to, n is the number system, an comma an minus 1 up to, so you go to a2, then you reach the 0 value. After this you actually have a floating point here, then you go to a minus 1, a minus 2, up to whatever. Karthik, is this slide visible?
Yes, sir.
So I request everybody to write this down and keep your notebook and pens ready, because now onwards we have to write a lot. If I'm going too fast, then just interrupt me, CRs. I will wait. So I will give more clarity on this slide once I go to the next one. The terms, please look at the terms. N is the number system. What is this small n and small n? N is the number of integer digits. That means you can see n here, n minus 1, a2, a1, a0. So till this point, we have integers, and this side is going to be fractions. So m is the number of fraction digits. So m will be from -1 to -1. So I think that is clear. You should be able to identify what are these terms. Then an. What is an? An is called as the most significant bit. That means in common words, so just try to say this now onwards, it is called as MSB. So most significant bit means it has got the highest place value. Highest place value. So can you identify an where it is? It is here. So this has got the highest place value, that is n. So this is going to be my MSB. AM is having the least significant bit value. So if MSB has the highest place value, LSB will have the lowest place value. So that is going to be LSB. Can you identify AM? So AM is here. So just excuse this minus sign, but the maximum value of n is here. And x is the radix or base of the number system. So where is this x? Can you see that every term has got a x? So first thing, x is here. And then so this is x. So you can see all the x values. So each term has got something associated with the radix. So if you have copied this, just type yes in the chat box. Okay, I have just removed the slide for 2 minutes just to download the attendance. So I'll take attendance at the start of the class and at the end of the class. In the online context, it is really unnecessary and not required, but just as a procedure we are doing it. So I guess we were on this side. So should we go to the next one?
Yes, sir.
So let's move on to the next slide. What is the characteristics of a number system? So I hope these points are now in your notebook. So please open this particular page when I'm going on the next slide. So the characteristics of a number system depends on certain points. So first thing here is the digits constituting in the number system. So for example, if it's a decimal, that is what we generally use, count from 1 to 10, it will be from 0 to 9. If it is, let's say, octal means there are 8 digits. So the digits will be from 0 to 7. If it is binary, then it will be just 0 to 1. That's it. So digits constituting the number system, that is one of the characteristics of the number system. Second is number of digits present in the number system. Number. Here it was digits. Digits means what? 0 to 9 are the digits. No, but number of digits would be in decimal. There are how many digits? 10. 0 to 9. In octal, how many digits are there? 0 to 7. So there are 8. In binary, how many digits are there? Only 2. So the characteristics of a number system not only depends upon how many digits but also which digits. Then the next one is, third point is maximum number that can be written with the given number. For example, if I have digits from 0 to 9, the maximum 2-digit number that I can write is 99. The maximum 3-digit number that I can write is 999. The maximum 4-digit number that I can write is 9999. So similarly, you can generalize that for octal. So the maximum number that you can write in octal is 77. The maximum number you can write in is 77. 4-digit number that you can write is 777. And then fourth, independent numbers used in the number systems. That means whether 0 is used 2 times, 1 is used 3 times, can we do that? That is also. So this part, fourth point, is generally something that we don't use much. We use only 1, 2 and 3 to characterize a number system. The fourth point tells us whether repetition of digits is allowed or not. That means 0 to 9 is fine, but can we use 0 2 times or 9 2 times? So that is, there was a lot of gray area with that. So we did not use that much, but definitely today's number systems are characterized by the first 3 points. So the number of digits used defines the type of the number system and is used to distinguish one system from another. This commonly referred to as the radix or the base of the number system. That means, let us go to this definition. Number of digits used. So when it comes to decimal, number of digits is equal to 10. Therefore, radix of decimal number system is 10. For octal, number of digits used is 8. Which are the digits from 0 to 7? So the radix of this number system is 8. Then we have binary or even hexadecimal. So binary will have a radix of 2 and hexadecimal will have a radix of 16. So we will come to that. So what this 10 means is that there are 10 digits used in the number system. 8 means that there are 8 digits used in the number system. 2 means 2 digits are used in the number system. And 16 means 16 digits are used in the number system. Now, what does the radix represent? The radix represents the weightage of each digit. present in the number system. So we'll just see that. For example, in a decimal number system, radix value is 10. So it is represented using 10 numbers of digits from 0 to 9. So let us look at this. Now, quickly, what you can do is, this table is there in front of you. So what you do is draw this table, but in this table show only these entries: 1, 2, 3 and 4. So I am giving you 5 minutes to draw this table. Karthik, is the table visible?
Yes, sir.
So once you have written this, write done. So you all can see here. So just don't draw this what I am drawing. But if you just see here, if I say number of digits, then how many digits are there here for binary? 2. Here there are 3 digits, 4. Here there are 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. You can see that from 11 onwards I have written A. So actually A is 10, B is 11, C is 12, D is 13, E is 14 and F is 15. So what you should compare is that the radix is equal to the number of digits. You can take any number system. Let's say a number system having only 6 digits, 0 to 5. So number of digits is equal to radix. So what is radix? Radix is nothing but the number of digits present in that particular number system. So what we are going to start with is decimal, because we count in decimal. Currently we are using decimal number system. If I tell you to write 99 today, probably you will be writing 99 instead of something in 1101, something like that. So we will start with decimal, then we will go to binary. So decimal is what humans use for counting. Binary is what computers use for counting. And that is why, since we are the designers of the system, we should know what is the conversions which are used from decimal to binary or binary to decimal. But sometimes these binary numbers can become too big. That is why we go for octal and hexadecimal number systems. So actually speaking, humans communicate in decimal, computers communicate in binary. But since we are only the inventors of the computer, we should be able to deal with these numbers easily. So for ease, we have octal and hexadecimal. So have you all copied this particular table? If you have copied, just write yes so that I can go ahead. Okay, so let's go ahead. So the commonly used number systems are, so you might write this: commonly used number systems are: first is the decimal number system, second one is the binary number system, then we have octal and hexadecimal. So, like I said, why do we use this? Decimal number systems used by humans. So we use, you can see our currency is also in decimal numbers. It is not in binary. If I write my number 10, if I write 10 rupees, something like this, 1010, I think person who does not know digital design will not be able to understand this. So if we start using binary, octal and hexadecimal in day-to-day life, I think we have to educate the entire population of India to read this thing, which is not possible. So everybody is taught decimal number system in school. So that is only the use widely. Then the next one is binary. So binary is used by computers. So sometimes the representation can become large, and that is why these are also used to reduce large binary numbers. Instead of saying used to reduce, we can say used to represent large binary numbers. So these two are more of a representation of this. So what you should remember, especially for the oral exam, which number system is used by the humans? So you should say decimal. And which is used by the computers? You should say binary. And to represent large binary numbers, we are using octal and hexadecimal. So this is what you should keep in mind. So let us look at the first number system. So right, decimal number system. It consists of 10 digits from 0 to 9. So that is why the number of digits is 10, and also therefore the radix is 10. So this is the general representation of any number system. So here instead of n, I am writing d base 10, and instead of ai, I am writing di. You can go back and see x was radix. X was the radix of the system. So since x was the radix, here the radix is how much? 10. That is why here I have substituted this x as 10. AI was the actual digits. So that is this. So AI can take any value, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So AI can take any of this value. So since this is, I'm using decimal, I'm just writing it as DI. So DI can take values from 0 to 10. So my dn to dn minus 1 can be any of these numbers. So the representation is something like this. That is, first is dn, we come to I is n into 10 raised to I is again n. So that is my first term, and my last term is d I is minus n. So I'm writing here d minus n into 10 raised to I is again here minus n. That is going to be 10 raised to minus n. So this is my most significant. I will not write bit here because in decimal number system using the word bit is not proper, but this is the most significant number and this is the least significant number. So for example we can see, if I want to represent this number 7368.121 in decimal, that is using any of these numbers from 0 to 9, this is my thousands place. The next one is 100, this is tens, this is ones, and the place value of 1000 is 10 raised to 3, the place value of 100 is 10 raised to 2, the place value of tens is 10 raised to 1, this is 10 raised to 0, anything raised to 0 is going to be 1. So here this is 1 plus 10 raised to minus 1. What is the meaning of 10 raised to minus 1? 10 raised to minus 1 is just 1 by 10. So this is 1 by 10, 1 by 100, and 1 by 1000. So this is the, and you can see 7 is in thousands place. So I am writing 7 into this, 3 into this, 6 into this, 8 into the next one, and then comes the decimal point. So this is somewhere here we have the point, that is the floating point, and then we have again 1 with negative indices of 10, 10 raised to minus 1, 10 raised to minus 2, and 10 raised to minus 3. So I hope you have all understood this, and I want you to copy everything on this slide. So I'll wait for 2 or 3 minutes. Okay, Karthik, can we go to the next slide?
Sir, 2 minutes.
Okay.
Yes, sir, done.
Okay. If others have also done, just type done so that I can be in sync with everybody. Okay. So anyways, we are recording, so don't worry if you are not losing out something. We can always Go back and see. Okay, so have you understood how to represent this number 7368? 7 into 10. So this is, we are very comfortable with this system because we have learned this in school. So instead of too much going into the formulas, what is my suggestion is, look at the examples. Example will give you a better idea of the formula. Since you are doing this for the first time, I have to show you the formula so that you can generalize later on. But as far as the actual use is concerned, please have a look at the examples. So the next system is binary number system. So here we have binary number system has two digits, that is 0 and 1. So here there is a correction. I think in copy pasting consists of two different digits, 0, 1. Again the formula is the same, but this time can you see that AI can take values of 0 and 1 and base is 2. So x is now replaced by 2. Now if you look at the formula, something similar to decimal, but now please note the radix is 2. The radix is 2 everywhere. So, and bn can be either 0 or 1. Even bn minus 1 can be 0 or 1. Similarly, b2, b1, b0, bi, b minus 1, b minus 2. All this can be, all the b's, all these values can be either 0 or 1. So I want you to copy this also. That is binary number system. Now just have a look at the example. If I want to write a binary number 1101.101, how would I write it? 1. So this is the first value is 2 raised to 3. The second is 2 raised to 2. This is 2 raised to 1 and this is 2 raised to 0. Similarly, this is minus 1, minus 2 and minus 3. So that's what we have done. First value 1 into 2 raised to 3. So what you should do is you should look at the floating point. So the first one will be 2 raised to 0 or radix raised to 0, radix raised to 1, radix raised to 2 and then radix raised to 3. And similarly after the floating point it will be radix raised to minus 1, minus 2 and minus 3. So in general you will have any number like this 1101.11. So here what you should keep in mind is first you locate the floating point. So right besides the floating point you will have radix raised to 0, radix raised to 1, radix raised to 2, radix raised to 3. And here you have radix raised to minus 1, minus 2 and so on. Now the question is what is the radix? So in this case the number of digits is 2 and hence the radix is 2. So that is why it will be 2 raised to 3, 2 raised to 2, 2 raised to 1, 2 raised to 0, point, 2 raised to minus 1, 2 raised to minus 2. So I hope you have understood the trick of locating first 0. First you locate this. This is where the floating point is. So here we have 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, and here you have minus 2, minus 2, minus 1, minus 2, and minus 3. If this number would have been something like this, 11101.11101. So here we would have 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4, and 2 raised to 5. So we would have to go till 2 raised to 5. And on this side, point, this would have been 2 raised to minus 1, 2 raised to minus 2, 2 raised to minus 3, 2 raised to minus 4, and 2 raised to minus 5. So that is what this is. Now, one more thing I will tell you here itself, but I will repeat it again later on. I just rub this. This was just for explanation sake. So here I have written the binary number actually 1101.101. But which number is this? Actually, which is this number? So if you look at this thing, the first term is 1 into 2. So 1 into 2 raised to 8. So that is going to be how much? 8. Plus, which is this number? 1 into 2 raised to 2. So 1 into 2 raised to 2 is 4. 0 into anything is 0. Plus 1 into 2 raised to 0 means it is going to be 1, plus 1 into 2 raised to minus 1 means what? 1 upon 1 by 2 plus 0 plus this is 1 into 2 raised to minus 3 means 1 over 8. So if you just sum this thing, 8 plus 4 plus 1 is 13, plus half is 0.5, and 8 would be I think it would be 0.125. So if I add this, what am I going to get? 13.625. So actually this number which is written here is 13.625, but in which value? Decimal. So this is the decimal equivalent of this particular number. So anyways, just I told you how to calculate binary to decimal here, but I am going to repeat this in a much detailed way later on. So can we go to the next slide, please? Karthik, Anushka.
Yes, sir.
The next system is octal. Again here, it consists of 8 different digits, that is from 0 to 7. Can you type the radix of this number system in the chat box? Can you all type the radix of this number system? Octal number system means what? 8. That is right. I can see Tanvi, Aditya, Pranav, Asmita, Richa, Apurva, Anushka, right. So Pranjali, right. So that is right. So 8 is the radix of this number system. So can you now generalize from this formula? Can you write the next formula now? So instead of n, I will write O8 is equal to summation I is equal to same minus m to n, but ai can take values of what? 0 to 7. So I will write here oi, and this time my radix x is equal to how much? 8. So that is why I'll write 8 raised to I. So this is what I'm talking about. So exactly 08 and 8. So similarly we have numbers from on to o minus n, but this time the radix is 8. So this indicates that each of these can take values from 0 to 7, and now you can see instead of b or anything else b, I have written o, and here now the x value has been replaced by 8. So just an example, the same example I have taken 7341.25 8. So now this is written as 7 into 8 raised to 3, 3 into 8 raised to 2, 4 into 8 raised to 1. So here we have the floating point. Then we have this 2 into 8 raised to minus 1. And then we have 5 into 8 raised to minus 2. So this part is the integer part. This part is the fraction part. So if you actually solve this 7 into 8 raised to 3 plus 3 into 8 raised to 2 plus 4 into 8 raised to 1 plus 1 into 8 raised to 0 plus 2 into 8 raised to minus 1 plus 5 into 8 raised to minus 2, and if you add all this, you can get the decimal equivalent of this number. So if you actually solve this, this value will be equal to the decimal number of 7341.258. You should also note here one thing, that you cannot write something like this. You cannot write an octal number to be 8341.25. Why you cannot write this? Because 8 is not a part of the octal number system. You cannot write, so this is forbidden. You cannot write like this 939.8.25. You cannot say convert this to binary or something, because this itself is not in octal first. This is where you are having 9 two times and 8. So 9 and 8 are not a part of any of the numbers in the octal number system. So now I am writing some numbers on the screen. You should tell me whether it is octal number or not. So by saying yes or no in the chat box. So I am writing a number here. Is this an octal number? If it is an octal number, you can write yes. If it is not, you can write no. Yes. So Ketan has said yes. Dhruwali has said yes. Okay. So many of you are saying yes. Now, why yes? That also you should find out. You should see each number here. 1 is used thrice, and then there is a 2. Are all the digits in this a part of this set? Yes. And that is why your answer is yes, it is a octal number. Now I am writing another number. You should tell me this. Is this an octal number? 0008. Is 0008 an octal number? No. So it is not octal number because though 0 is a part of the subset of these numbers 0 to 7, 8 is not a part of this subset. So that is why this is not a octal number. So I hope you are now getting how to actually identify whether this number is a octal number or not. So I could see many responses from Nishita, Yash, Rucha, Kashmira, everybody. Good. So now let's go to the next number system, that is hexadecimal number system. So I'll give you 5 minutes to write down this. So now here the radix or base, that means x is equal to 16. That is why here x is 16, and ai can be any number from 0 to f. Now a has got value 10, b has got value 11, c has got value 12, d has got value 13, e has got value 14, and f has got value 15. That means if you find e here, the value that you will write here is 14. So it is 14 into 16 raised to minus 1. So I'll give you 5 minutes to copy this. I hope this is self-explanatory now. That is, this will take values from 0 to 15. But when we write, we'll write it as a. And you can see now the x values are 16, this is the maximum place value, this is the minimum place value. So in this is having the maximum place value, this is having the minimum place value. So here it is b. B means what? 11. So here it will be 11 into 16 raised to minus 1. Okay, so have you completed copying this? Karthik, Anushka,
Yes, sir.
I'll wait for another 1 minute and then go ahead. So at least now you are able to represent the numbers and identify whether the number is a belonging to a particular number system or not. Now I am writing a number here. You have to tell me whether this number is a hexadecimal number or not. So is this a hexadecimal number? If it is an hexadecimal number, you can just type yes. If it is no, you type no. Okay, so this is a hexadecimal number because each of the digits in this are a part of this particular number set. Is this a hexadecimal number? If yes, then you type yes. If no, you type no. Yes, of course. So we can say that any number probably if I write now, it will be a part of a hexadecimal number system because hexadecimal number system has got the most number of digits. That is the radix is 16. So let us go ahead. Now comes very famous. So I want all eyes on the screen, and this is something that is asked for around 15 marks in your main exam. So that is the conversions between binary and octal and then hexadecimal and so on. So let's have a look at it. Human beings use decimal number systems while computer uses a binary number system. Therefore, it is necessary to convert decimal numbers into its binary equivalents while feeding numbers into the computer. That means even if you know 1, 2, 3, 4, while giving input to the computer, you have to give it as 1010. That means you have to convert from decimal to binary. So while feeding something to the computer, you have to convert decimal to binary. Similarly, it is also necessary to convert binary numbers into decimal equivalents while displaying result of operation. For example, you can see that at the station there are indicators and it displays the time and the number of the train and where it is going to go using decimal number systems. So if the display is something like, if I want to represent number 10 in binary, it is going to be something like this 1010. So naturally what will happen, display wise also, to display 10 I require a smaller display, but to display 1010 I require a bigger display. At the same time, everybody is educated enough to read this 10, but not all will be educated to read this as 10, 1010. So that is why I told you the real world is analog and which will have lots of values. If people will not understand this. So that is why while displaying result, you have to convert binary numbers into its decimal equivalents. So that is necessary. I hope you have got this point. Though we are going to binary, computers are computing everything in binary, but while displaying, we have to again display the original values. So hence there is a need to convert from decimal to binary and binary to decimal. So reverse operation is also required. However, dealing with a large quantity of binary numbers of many bits is many times inconvenient for human beings. So that is why the number 10 in hexadecimal is just represented by one letter, that is A. So can you see the representation of this 10 became very small when it came to hexadecimal. So instead of saying 1010, I can say 8. It means the same thing, that is 10. That is why for our convenience, convenient for human beings, technology should be a slave of human beings, not the other way around. So for our convenience, we have designed this. Therefore, octal and hexadecimal numbers are used as a shorthand means of expressing large binary numbers. So let us see how to convert decimal numbers into any radix. How to convert decimal numbers into any radix. That means I am talking about decimal to binary or decimal to octal or decimal to hexadecimal. So we will now be dealing only with these four, that is decimal, binary, octal and hexadecimal, not other binary systems. So this can be carried out in two steps. It can be carried out in two steps. Why two steps? Because many times number has got an integer part and a floating part. So something on this side of the floating point and something on this side of the floating point. For example, you may have 10.9. So you have an integer part and you have a floating part. So we have to address both. Both needs to be converted to binary. And that is why we do it in two steps. First one, conversion of integer part by successive division method. That means integer part, we use successive division method. So the word itself means successive division means whatever is the integer part, we keep on dividing by that particular radix. And here conversion of fractional part by successive multiplication. So we keep on multiplying by that particular radix. So what this is what now we will see. First is conversion of decimal to binary. Do you want to copy this? Karthik, Anushka?
Yes, sir.
Okay, I will be on this slide for 1 or 2 minutes. So what you need to only do is, you can just write conversion of decimal to any radix. Point number 1, conversion of integer part by successive division method. And point number 2, conversion of fractional part by successive multiplication method. So I think I'll go to the next slide. So first we'll see conversion of decimal to binary. So let us take an example directly. So I want you all to write down conversion of decimal to binary. So this is the way in which in the exam also they will give you many questions and write 24.6. So they have already given you the radix, that is about 10. That means this number which is given to you is a decimal number. Convert that to a number having radix 2. That means convert decimal to binary. So this is the way of asking you to convert a decimal number to a binary number. They will always specify the radix. If they don't specify the radix, sometimes they do printing mistakes in the paper and they forget this. So you will get full 5 marks for this, whatever you write here. Are you understanding? So based on your interpretation, whatever you write here, you get the answer. So mostly this mistake doesn't happen, but if it happens, then you get the advantage. But here, this is the base is 10. That means they are explicitly asking us to convert a decimal number to a binary number. Okay. So I'll go ahead. Step number 1. Right, everybody. Step number 1. Step number 1. Separate integer part and fractional part. So just to be sure, is everybody writing with me? Just write a yes in the chat box. And if is my speed okay? If my speed is okay, just type okay. Okay, so separate integer part and fractional part means, see what I have done. I have written here the integer part is 24 and the fractional part is 6. So I have written here 24 and fractional part is 0.6. Now what I have done, step number 2, write down with me. So first step was pretty simple, separate integer part and fractional part. So just by looking at the number, you can say this is integer and this is fractional. Anything on this side of the floating point is fractional and on the left side it is integer. Right, step number 2. Find the binary equivalent of integer part using, very important, successive division method. And very commonly, when you convert from decimal to binary, that time this successive division method is also called as double double method. So it is only for decimal to binary conversion. When you are doing successive division, it is called as double double method, because now you will see why it is called as a double double method. So what we do, so this is how you can write in the exam in this table, but I have just simplified the things in this table. So you may not write this table in the exam, you may simply write this and directly convert and say that this is the binary equivalent. Now, what I have done, now we are dealing with which part in step number 2? We are dealing with integer part, and the integer part is 24. So what I did is I wrote this 24 here. My radix here is 2. So they are telling me to convert to binary. That is why my divisor is 2. So the integer part is 24, the divisor is 2. Now if I divide this 24 by 2, the quotient is 12. That means I'll get 12 here. So 2 into 24, 2 into 12 is going to be 24, and the remainder is going to be 0. So I write that. Then this 12 Again I take here and again I divide by 2. This time 2 into 6 is going to be 12. So I write 6 here and again the remainder is 0. Again I take this 6 here and divide by 2 to get the quotient as 3 and remainder as 0. Again I take this 3 here and divide by 2. But this time 3 is not exactly divisible by 2. So that is why 2 into 1 is 2. But now this time the remainder is going to be 1. So now what you can see here is this same operation. I have written it in this way here. I started with 24. I divided 24 by 2. I got 12 and I wrote the remainder here. Then I again divided 12 by 2. I got 6 and I wrote the remainder here. I again took this 6, divided it by 2. I wrote this quotient here, remainder here. And I again took this 3, divided by 2 and wrote the integer part here and the remainder part here. So now what is the binary equivalent of this 24? So you go in this way. You start from 1 1 0 0 0. Go upwards. This bit will be your MSB and this bit will be your LSB. This is the standard convention that you have to follow. And we will verify this also whether this is the really 24 or not. So this 1 1 0 0 0 becomes the binary equivalent of 24, not 0.6, only 24. So the binary of 24 is 11000. Now we can slightly verify this. You can see that there is no decimal number in the integer. There is nothing after the floating point in the integer part. So we can write 1 into 2 raised to 4 plus 1 into 2 raised to 3 plus 0 into 2 raised to 2 plus 0 into 2 raised to 1 plus 0 into 2 raised to 0. So all these three terms will become 0. But this term 2 raised to 4 will be 16 and 2 raised to 3 will be 8. So 8 plus 16 is going to be 24. So you can verify it like this whether your answer is correct or not. I hope you have got this term. So please copy this table. So you have two options. Either you can copy this table or this table. This is only for understanding sake. You can directly do this in the exam and write like this. No problem. So 24 gets divided by 2 and then you write the remainder quotient here and then remainder here. Again this gets divided by 2. Write the quotient here, remainder here. 6 gets divided by 2. Quotient here and remainder. So I hope you have understood this technique. Kashmira, Karthik, just let me know once you finish off. So what we actually did is we converted the integer part of the decimal number into the binary part. Now I am going to the next slide. This thing is getting recorded anyway, so we'll go to the next slide. Now what will change is, this is step number 1. We separated into integer and fraction. Now right now we dealt only with the integer part, but now we have to deal with the fractional part also. Please recollect, in integer part we have used successive division. So what we will use in for fractional part? Successive multiplication. So that is what we are going to use. So in step number 3, you can write step number 3. Don't write this. Just write step number 3. Find binary equivalent of fraction part using successive multiplication method. So now in step number 2 we dealt with the integer part. In step number 3 we are dealing with the fraction part. Somebody is not on mute. I can hear some voices. So if you have any questions, you can raise your hand and ask me questions. I am ready for those questions. Or probably you can ask me towards the end. So have you understood this? Now, going back to step number 3. Now what we do is, we start with the fraction part 0.6 and the radix is again 2. So in step number 2 we were dividing by 2. Here we are going to multiply by 2. 0.6 into 2 is 1.2 and the integer part of 1.2 is 1. So what I'll do is, I'll just write I is equal to 1. So this part I'll write it here, and what remains is 0.2. So you can see that this 0.2 I took it on the next step and again multiplied this by 2. This time 0.2 into 2 is 0.4. But in 0.4 the integer part is 0. So I wrote integer part as 0. So integer part I have taken it here, and 0.4 again I multiplied by 2. So that is what we mean by successive multiplication. You keep on multiplying the fraction part by 2 till you get some integers. So 0.4 into 2 is 0.8. Again the integer part is 0. 0.8 into 2 is again 1.6. This time integer part is 1. And now you can see this 1.06 is again coming here. So it is kind of a iterative thing which will keep on happening. So what we can do is, we can just do this 5 times as a thumb rule. If you have to calculate the binary equivalent of the fractional part, how many times will you successive multiply? At least 5 times. The thumb rule is how many times? At least 5 times. So now in step number 2 you are going reverse, but in step number 3 you have to come down. So this is going to be your MSB and this is going to be your LSB. So MSB is 1, then you have 0, 0, 1, 1. So here the binary equivalent of the fractional part is going to be 1, 0, 1, 1. So integer part was 1, 1, 000, which we checked also. Here also you can check. This is 2 raised to minus 1, 2 raised to minus 2, 2 raised to minus 3, minus 4, minus 5. You should get around something like 0.6. Now, once we do this, we have to combine. So we have to now combine integer point fraction. So we have calculated the binary equivalent of integer part. Now we have also calculated the binary equivalent of fractional part. Binary equivalent of 24 is 11000. Binary equivalent of 0.6 is 1001. So we will write here integer point fraction, and then here we will write integer part point fraction part. So that is what is clearly given in this step. That is the decimal equivalent, the binary equivalent of 24.6 is 11000.10011. So this is the answer. So while writing the answer, you should write completely. Don't just leave like this. You have to write 24.610. Now this question mark you have calculated. So that is going to be this number. That is 11000.10011. So this is the way to write the answer. So now you can copy step number 3 and then write this and then write the answer. Have you all understood this particular method? If you have understood, just type a yes.
Yes, sir.
Yes, sir. No, sir. No.
Yes. So
Sir, Gaurav is having a doubt.
yes, Gaurav, tell me.
Yes, sir. Sir, in step number 3, how did
Yes.
0.2 in step number 3?
In step number 3,
Yes,
how this is 0.2? Okay. So this is when we multiplied 0.6 into 2. So we did like this: 0.6 into 2, we got 1.2. What was the integer part of this? 1. So I wrote I is equal to 1. What was the fractional part of this? 0.2. So I wrote 0.2 into 2. Next is 0.4. So this 0.2, the fractional part, I wrote it here. Have you understood this, Gaurav?
yes, sir. Yes, sir. Thank you.
And again I multiplied, I got 0.4. I wrote integer part is equal to 1. And then again this 0.4 I wrote it here. I did into 2. I got 0.8. Again I wrote integer part is 1. Then again I wrote 0.8 into 2. But this time I got 1.6. So this 1 I wrote it here. I is equal to 1. And this 0.6 came here. Have you understood, Gaurav?
Yes, sir. Yes, sir. Thank you.
Yes. Please ask doubts. Even if you have very small doubts, please ask them, because those might be the doubts of everybody, and it will help everyone. Yes.
So, how to know like when to stop continuing to multiply?
Yes. So I told you that as a thumb rule, you have to do it 5 times, minimum
Okay,
5 times.
okay, okay. Thank you, sir.
Yes. Yes. Anybody has more doubts? Please ask. This is the basic thing that you should know. Okay. Should I move ahead?
Yes,
So
sir.
before moving ahead, what I will suggest is we will take a small break of 15 minutes. It is already 12 o'clock and you have been sitting for 2 hours. So I don't want you to bug you more. Uh, if I am here for 15 minutes, but you all can again rejoin at 12:15. So if you want, you can just mute and go and come back at 12:15. You don't even have to leave and go. Is it fine, Karthik, Anushka?
Yes, sir.
I think 15 minutes break is required for everybody. So I am just removing this. I'll be sharing this PPTs with you, so don't have to worry. But I will send you a nice formatted PPTs, not this on which I have written. I will send you good ones, which you can just scroll down and again relook at the procedures. Karthik, can you see this?
Yes, sir.
Have some coffee, tea, and come back.
सर एक्चुअली एक क्वेश्चन पूछना था
Yes.
सर स्टार्टिंग में हम लोग ने जो ग्राफ देखा ना उसमें जो सेकेंड लास्ट ग्राफ था उसका नाम हाँ क्वांटाइज सिग्नल से डिजिटल सिग्नल में जब कन्वर्ट होता है तभी ग्राफ में जो नंबर्स दिया था उसमें अभी क्वांटाइज सिग्नल में 2 3 2 ये सब नंबर्स दिख रहा है एंड डिजिटल में 1 0 1 1 1 सो ये तो बाइनरी में कन्वर्ट हुआ ना
Right. So we converted the analog value to binary.
सर बट वो कैसा होता है मतलब अभी हम लोग डेसिमल से बाइनरी कर रहे हैं
I got it. So that is done using a device called as an A to D converter. A to D.
मींस एनालॉग टू डिजिटल कन्वर्जन
Yes. So so the conversion part, that is sampling, quantization, and A to D conversion. This part will be dealt separately in another subject. We are going to deal with digital signals and digital systems. So I am going to assume that my signal is going to be already digital. Somebody will be giving me digital signal only. I don't have to take the pain to convert it. Though in reality, you have to do it. For example, if you have a HC ultrasonic sensor, so the ultrasonic means what? The sound waves are falling on the sensor and that is getting converted from analog to digital. Then only your Arduino microprocessor can process that signal. So that sensor come A to D converter that we buy for 50 or 60 rupees. So that does this job of sampling, quantization and A to D conversion.
एंड सर देन डिजिटल टू एनालॉग में कन्वर्ट करने के लिए ये पूरा प्रोसेस बैक होता है क्या मींस
Yes.
पूरा रिवर्स इसमें होता है क्या
Yes. So for that you require D to A converters.
ओके
So basically this part is not digital. It is not completely digital nor it is completely analog. So that is why we call this as mixed signal design. So this is a subject for you in semester 8. Mixed signal design. So this is you are going to deal with these signals also, but not in this course. In a course called as mixed signal design, which probably I only will be taking for you. But in semester 8, long way from now.
एंड सर पल्स कैरियर सिग्नल का काम क्या होता है
It is used to take the sample. It is just used to multiply.
ओके
So if you multiply these two, here there is a value, here the value is 1. So value into 1 is the value itself. And here value into 0 is going to be 0. So depending upon what is the frequency of this signal, if you choose a higher frequency carrier, you can take more samples in less time. If you choose a low frequency carrier, you can take lesser samples.
ओके
But again, this sampling, quantization, and A to D conversions, these techniques are generally dealt with in subject called as LICD. So just to give you a flair of how to come from analog to digital, I put all the things on one slide here so that it gives a brief overview of how from where exactly this digital signal comes. Because in nature nothing is digital, everything is analog. So how it comes, how digital signal comes, just to give you a flair of that, I made this slide.
वो
So
स्टार्टिंग का चार ग्राफ समझा लेकिन वो फिर बाद में डिजिटल में अचानक कैसे कन्वर्ट हुआ
so that is using A to D converters. A to D converter. So don't worry about it, it's not relevant in this course. Okay. Okay, so let us start our next session of around 30 minutes, and we'll continue with our previous thing. What we had done before was we saw the conversion of decimal to binary. Now we will see the other way around. Karthik, can you hear me?
Yes, sir.
Okay, so while others join, we can just start. Okay, so what I have done is I have taken from the previous slide itself. So you can see that this was our final answer. That is 24 point. This was the final answer that we had. So what I am doing is I am taking the same answer and we will reconvert it back to 24.6. So now we will start with this value and try and see whether we get the same value back. So that is the first thing. So the question now is convert 11,000.10011 in binary to decimal. So now we are looking at conversion of binary to decimal. So what I did is I'm just magnifying this. So in the next step, this is just the magnified version of the given problem. Now you can see you have to identify the place values. So this is going to be, so the place value of this 0 is going to be 2 raised to 0. Why? Because the radix here is 2. Here the place value is 1. Why? Again the radix here is 2. So now what I do is I multiply this 1 with the place value. So 1 into 2 raised to 4 is the first term. Then we have 1 into 2 raised to 3, that is the second term. Then we have 0 into 2 raised to 2. Karthik, can you quickly check whether recording is on?
Yes, sir, it's on.
Okay. Then we have the third one, that is 0 into 2 raised to 2, that is the third term. Then similarly fourth is this one. Then we have fifth. So once we reach here 0 into 2 raised to 0, we are changing over to the negative indices, that is 1 into 2 raised to minus 1, 0 into 2 raised to minus 2, 0 into 2 raised to minus 3, 1 into 2 raised to minus 4, and again this 1 into 2 raised to minus 5. So in all there are how many digits? 1, 2, 10 integer part and 10 in the floating part. So there are 10 digits in the integer part, 5 digits in the integer part and 5 digits in the fractional part, in all 10. So you should have these 10 terms. So this is 1, 2, 3, this is 4, 5, 6, 7, 8, 9 and 10. So many times what I have observed is that when the numbers are big, students skip one of them and they create a problem in the answer. So that is why you should do a checkpoint here, that if there are 10 digits here, we have 10 terms here also. Going ahead, you can see that 2 raised to 4 is 16, 2 raised to 3 is 8, anything into 0 is 0, anything into 0 is 0. So for these 3 terms, we get these 3 zeros. Then we reach here. So this is actually 1 into 2 raised to minus 1 means 1 by 2. So this is going to be 1 by 2. Again, these terms are having zeros. So you get 2 zeros here. This is 1, 2 raised to 4 is 16. 2 raised to minus 4 will be 1 upon 16. And similarly, 2 raised to minus 5 will be 1 over 32. Now it is time to remove your calculator and actually calculate these values. So can you type the value in the chat box? Right. So Divya is the first one to give the answer, followed by Prathamesh. 24.59375. So we have seen that this was actually 24.6. So 24.59375 is pretty close to 24.6. So in the exam, you don't have to worry about what this original thing was. You have to only calculate this in this way and write 29.59375. That's it. Here also, thumb rule will be you have to write this up to 5 digits. You have to write this correct up to 5 digits. So that is good. So just for others, I have done the calculation here. 16 plus 8 is as it is, and half is 0.5. 1 by 16 is 0.0625, and 1 over 32 is 0.03125. When you add all this, you get the total fraction part as 0.59375, which is pretty close to 24.6, and that's what is the answer. So you have to write the answer in this form. That is, answer is whatever is the given, instead of question mark, you will write your answer 24.59375 10. So this is the way to write answer. So has everybody copied this thing?
Sir, Apurva has a doubt.
Yes, Apurva. Apurva, you can unmute and ask the doubt.
Actually, that was by mistake.
Okay, so where did you actually go wrong?
No, sir. Actually, my computer is lagging behind.
Okay, so maybe that might be because of internet connection. But are you
Yes.
getting this answer 24.59375?
Yes, sir. Yes, sir.
Yes, then you are right. So as long as answer is right, it's all fine. Anyways. So now I am going to the next one. Now we did conversion from decimal to binary, and then we did from binary to decimal. Now let us look at decimal to octal. So this is the next question, that is 35.45. Again, the value given to us is radix 10. That means value given to us is in decimal. Now instead of binary, they want it in octal. So again, step number 1 is separate integer part and fractional part. Please write down this. So the integer part is 35 and the fractional part is 0.45. This is fractional. So this step is the same in all decimal to binary, decimal to octal, decimal to hexadecimal, everything. This step is going to be the same. Step number 1 is same for all the conversions. When you are doing from decimal to any other. Then step number 2, find this time not binary equivalent, octal equivalent of integer part using successive division. So what is common as before? Integer part we are using successive division. For floating part or fraction part we will use successive multiplication. But this time we want not binary equivalent, we want octal equivalent. So it is not divided by 2 anymore. Successive division initially was by 2, but now it will be divided by 8. So coming back to this, so my integer part is 35. So I write 35 here. Divisor is initially was 2, now it is 8. So 35 divided by 8 is 32. So what remains is 38 for the 32. And what is the remainder? 3. Now 4 is not further divisible by 8. That is why we leave it as it is. Similarly, here also you can see 8 into 4 is 32. So 35 minus 32 is going to be 3. I hope you have understood this part. Do not write this. Simply this much. So for this quotient now is not further divisible by 8. We have reached the limit. So now we can write same way. You have to start from the lowermost value and go at the top. So this becomes my MSB and this becomes my LSB. So what is the value of 35 in decimal of the 35 decimal in octal? That is going to be 43. That is, don't call it 43, you call it as 438. Because when you say 43, it means decimal. But when you say 43, it means okay, it is octal. Like how you say 10, like this you should like that you should say 43. Don't say 43. So I hope this part is clear. Whatever is the integer part, initially we were dividing by 2. Now we have to divide by 8. Quotient is 4, remainder is 3. Again the same thing. Start from the MSB, go to LSB and write it down. Now step number 3. Do you want to copy this table? Karthik, Anushka, others?
Sir, copied.
Okay, this table is pretty small as before, and it is very obvious that when you divide a number by bigger numbers, you have to divide less number of times. That is the major advantage of it. So if you are dividing it by 2, 2 is a smaller number as compared to 8. So that is why it is 4 times smaller. That is why you are, when you divide, you have to divide also more number of times. So in a way, in decimal to octal, you have to divide less. Okay. Now you write step number 3. Again, I am comparing it with binary. First, in step number 3, we have written here binary equivalent of fraction part using successive multiplication. So fraction and successive multiplication is now the same. Only we are finding out now not binary. Now we are finding out octal. So now the multiplication previously was with 2. So we were multiplying the fractional part with 2. Now we have to multiply it with 8. So starting with this 0.45 into 8. So you take this 0.45 multiplied by 8, you get 3.6. Now integer part is 3. And the fraction part that remains is 0.6. So that will come here. Now you take that 0.6, again multiply by 8. What you will get is 4.8. The integer part of this 4 will come here, and this 0.8 will again come at the next step. So like I told you, as a thumb rule, you have to do this at least 5 times. So 0.8 into 8 is 6.4. Again the integer part is 6. 0.4 into 8. So here what remained was 0.4. The 0.4 came here. Again that you multiplied by 8, that is 3.2, and the integer part came on this side. Again the floating part is 0.2, that came here, multiplied by 8, you got 1.6, and 1 you got on this side. So again, similarly, you have to go from top to down as in binary. This is your MSB. This is the LSB. 3 is going to be your MSB. 1 is your LSB. So your octal equivalent of 0.45 will be 34631. So it will be 34631. So this is the octal equivalent of integer part. This is the octal equivalent of fractional part. Now you will write it as integer point fraction. Integer point fraction would give you this. 43 I will write it here, and 34631 I will write it after the floating point. But while writing the answer, you have to use this 35.4510 is equal to 43.34631 radix 8. So while writing the answer, you will write the answer in this way, 35.4510. Very clearly you are stating that given value is in 10 and I have converted it into octal. Please note that every value here is less than 7. 7 or less than 7. So 433461 all fall in the range from 0 to 7. So this is an octal number. Any doubts in this? So I'll give you 2 minutes to just copy this thing. So decimal to anything or anything to decimal, we have to use successive division and successive multiplication. So I'm going to the next slide now. So we did conversion of decimal to octal. Now we need to see octal to decimal. So we can start with this number itself. Now what is given to us is the number in octal. We have to convert it into decimal. Octal to decimal. So again, I just magnified what is given. In the previous slide, I had written here 2 raised to 0, 2 raised to 1, or 2 raised to minus 1. But here now the radix is 8. That is why it has to be 8 raised to 0, 8 raised to 1, 8 raised to minus 1, 8 raised to minus 2, and so on. So again, like I told you, checkpoint. How many digits are there? 1, 2, 3, 4, 5, 6, and 7. So I should have 7 terms. 1, 2, 3, 4, 5, 6, 7. So I should have 7 terms while I add. Now first 4 into 8 raised to 1, that is my first term. 3 into 8 raised to 0, second term. Then 3 into 8 raised to minus 1, third. 4, 5th, 6th, and finally we have 1 into 8 raised to minus 5. So can you solve this on your calculator and tell me what is the answer? Just type the answer in the chat box. Yes, I forgot to acknowledge Hemant. Hemant had given the right answer well before I even explained it. 43.3461. Good. So should I give you a clue? The next step would be this. That is right. Mohammed test is right. 35. Even Bhuvan is right. So see, Divya has given the answer 35.4499 and Mohammed has given the answer 35.44998169. So it is okay. I mean, when we check, we will see roughly whether you are close to the answer or not. So we will not go too much into it, but yes, the answer should come close. Even Asmita and Mohammed have got almost the same answer. So I think the most correct answers are from Asmita and uh, Mohammed Kaif. Okay, fine. Druvali answer is also right. Suman's answer is also right. 35.44 is fine. I mean, it's close. So this is the actual thing if you solve it. So actually, if you see, these values don't make much difference on the answer, but these two will. So that is why I always say go up to 5 decimals. So in the exam, they may cut short. They may not give you higher decimals because they also know that these answers will generally not affect the main answer. So that is 35.449. So you can take it as 35.45. That was our previous answer. That is right. So Amit has got 35.44998. So 449 can be made 45. So that is absolutely right. But in the exam note, do not round up. Write whatever you get. So whatever answers you have posted in the chat box, according to me, all answers are right because they are very close to the real answer. So that is fine. In engineering, we excuse such 3 or 4 decimal mistakes unless you are calculating the distance to Mars or something like that. So at that time, this error is also not uh, acceptable. You have to go at least up to 12 digits, 12 floating point numbers or at least 15 floating point numbers. Okay. Now answer would be like this: 43.3461 is 35.41 in decimal. Next, conversion of decimal to hexadecimal. So can you all start this now? So first two steps. First step number one is same. That is separate integer part and fractional part. This time you will divide 22 by not 2, not 8, but you will divide by 16. And while multiplying in step 3, you will not multiply by 2 or 8, you will multiply by 16. So step number 2, find hexadecimal equivalent of integer part. So this is decimal to hexadecimal. So you are now finding hexadecimal equivalent again of integer part using successive division. This time division is by 16. So what will be the hexadecimal equivalent? 16, 1 6. Don't call it 16, you call it 1 6. Radix 16, 1 6, radix 16. So this time this 22 comes here. We divide that by 16, so you can divide 22 only once by 16, that is 1, and that is the remainder will be 6. 22 minus 16 will be 6, and you can't divide this further. 1 is less than 16. So this becomes your MSB, this becomes your LSB. Similar thing is shown here in this table. So Karthik and Anushka, can we go ahead? Kashmira, can we go to step number 3?
Yes, sir.
Kashmira?
Yes, sir.
Okay.
Sir.
Yes?
Yes, sir.
Okay, fine. So now I am going to step number 3. So you can see that integer part I have just kept it there only. Now I want you all to calculate the floating part. Great. So Karthik has already come up with the answer 16A3D7. Atharva also has come up with the answer. So I want you all to calculate the floating part quickly. So just to start, first will be 0.64 into 16. So here you get integer part as 10. But there is no 10 in hexadecimal. After 9 there is A. So I write A. Then 0.24 into 16 will give me 3.84. So this 3 would come here, and 3 is very well there in hexadecimal. Then we have 0.84 into 16, which is 13.44. So this is 13. And even 13 is not there, but instead of 13 we can write D. And then 0.44 into 16. So that gives me 7, and 0.04 will come here, and here finally you get a 0. So as a thumb rule, I told you have to do this at least 5 times. So 10 is my MSB, 0 is my LSB, but actually while writing 10, I will write A, and while writing 13, I will write D. So you can see instead of 10 and 13, I have written A3D 7016. So again combine this. So this is going to be your final answer. Yes, I can see Dhanashri, Kashmira. Kashmira, you have to add that 0 also. I think you did only 4 times. If you do 5th time, you will get a 0. Even Mohammed Kaif, I think you multiplied only 4 times. If you multiply this 5th time, you will get 0.64, and that part will be 0 here. So just add that one small thing there at the end. Okay, great. Asmita is Tushar. Yeah, well, I can see some new names. Ganesh, yes. Prathamesh. Month, right. Great. So this is going to be our final answer. That is 22.6410 into 16.83D70. Pratik, how did you get 22.63999? Yes, so Vishwas has got a very good question that what if the number is minus 22.64? So generally what we do is to address a minus, first we do this as it is, whatever we do. So whatever is the, let us say this is the equivalent of 22. So what I do is to address a minus sign, I can put a 0 here. And if it is, if it's a minus, I'll put a 1 here. And if it is a plus, then I'll put a 0 here. So actually we add some more bits to address that 1 and 0, or positive or negative. Vishwas, I think I have answered your question. Vishwas, you can unmute and
Yes, sir. Got it.
okay. But let us not consider this for now, because
Yes.
this will come slightly at a later stage. I will address this.
Okay.
Because if you see, whenever we are writing 22.64, I am appending a 0. So when I append a 0, my value doesn't get affected. So this is, so place value wise, if I add 0 here, 22.64 doesn't get affected. But if I write a 1 here, if I write a
Then
1 here, then this value will get affected. So
yes.
it is important to see it in this way. That means it is 0 or 1, positive or negative, and then whatever is the value of this 22.64.
Yes, sir. Yes, sir. Got it. Yeah. Thank you, sir.
Okay. So now I want you all to convert this thing. Divya has already given the answer 22.6399, which comes pretty close to 22 point our answer. So this is conversion of hex to decimal. So I'm just going through it. Now you can see that the place values are powers of 16, not 8, not 2. So again, there are how many terms? 7 terms. So there are 7 terms in the addition. Now specifically, I have written this step. This A has to be considered as 10. This B has to be considered as 13. So A is 10, B is 13. So when you have this here, now I think these are all numbers and you can put them in the calculator and calculate the answer. So you will get this 16 plus 6 plus 10 over 16 plus 3 upon 256. So that is going to be the answer, 22.63977. So good, many of you are getting that answer. So I have just approximated it to 22.64, and you can write this, or you can also write it as 22.63997, whatever you have got. Now, after doing this, we are ready to see this conversion table actually. So I want each one of you to draw this conversion table in your notebook, because tomorrow we will require this conversion table and it should be there in front of you when you are actually calculating something. So the conversion table is very simple. You write decimal, binary, octal, hexadecimal. You write here 0 to 15, binary. So how did I get these numbers? So I took 4, I divided it by 2. 2 2s are 4, remainder is 0. Again 2 1s are 2, remainder is 0. So 4 is 1 0 0 1 0 0. So the equivalent of 4 is 0 1 0 0. If I take 15, if you take 15 and keep on dividing it by 2, so 2 sevens are 14, remainder is 1, 2 threes are 6, remainder is 1, 2 ones are 2, remainder is 1. So the binary equivalent of 15 is going to be 1 1 1 1. So like this, I have populated this table, but if you want to just observe, you can see from 0 to 7, first 8 numbers 0 to 7, the digits are 0 0 0, then all ones. Then you have 4 zeros and 4 ones, again 4 zeros and 4 ones. Then you have 2 zeros, 2 ones, 2 zeros, 2 ones, 2 0, 2 ones, like that. And then you have 0 1 0 1 0 1 0 1. So just to write it fast, you can follow that pattern. And then we have octal and hexadecimal. So this is, so I showed you how to convert from decimal to binary, decimal to octal, and decimal to hexadecimal, and even vice versa. How to go from here to here, and from octal to decimal, and how to go from. So these conversions are always possible, but what we will do is we will just tabulate this, and if you want, you can verify this later on. Now, what we have not seen is, which will not be a part of today's discussion, what we have not seen is, if I have binary, how do I directly go to octal? Okay, decimal to binary we have seen, decimal to everything we have seen. How to do this? Or if I have octal, how to go to hexadecimal? So these conversions we have not seen. So that is what we will see this tomorrow. All these conversions, that is binary to octal and hexadecimal, binary octal to binary, and binary to hexa, and so on. So Karthik, Anushka, has everybody drawn this table? If you have drawn this table, just say yes.
Sir, 2 minutes.
Yeah. So I hope you are enjoying these sessions and my speed is okay. Initially, I'll go a little bit slow, and towards the end, we can go fast. Once everybody is comfortable with these concepts, then it is easy for me also to go fast. But initially, we will go slow. Some of you might be already knowing this, but keep it to yourself. Many of you might be doing it for the first time. Yes, Vishwas has a question. Sir, is that code 8421 code? Yes. So binary code is a 8421 code. So this is actually a 8421 code. But when we will look at some more codes like 2421 and so on, so at that time we will say that okay, what we studied initially was a 8421 code. Does that answer my question, Vishwas?
Yes, sir.
Okay. So I think we will conclude here. Just do not log out. I'm just taking out the attendance. So please bear for 2 more minutes. So great. There are 71 plus 74 students. Okay. So I'll be here for another 5-10 minutes. If you have any questions, you can ask me, or you can log out. Next week we'll come at same time and try to finish off chapter number 1. But if it doesn't, don't worry, we'll just do it next time. So that's it from my side for today. Anushka and Karthik and Srishti, I'm done for the day.
Thank you, sir.
Thank you,